context-free grammar, sometimes all the production rules and symbols are not needed for the derivation of strings. Besides this, there may also be some null productions and unit productions. Elimination of these productions and symbols is called simplification of context-free grammar. So we have studied about context-free grammars, and in those grammars, sometimes all the production rules and symbols are not needed for derivation of strings. So we can eliminate those unnecessary productions and symbols, and that is called as simplification of context-free grammar. Also, there may be some null productions and unit productions. Now, the meaning of this null productions and unit productions, I will explain it to you in the coming lectures, so don't worry about it. And so, elimination of these useless productions and symbols is called simplification of the context-free grammar. And the simplification consists of the following steps. It has mainly three steps. One is the reduction of CFG, which we will be studying in this lecture, and then we have the removal of unit productions, and then we have the removal of null productions. So these two we will be discussing in the coming lecture. So in this lecture we will be studying about the reduction of the context-free grammar. Okay, so let us see how we can do this reduction of context-free grammar. So reduction of CFG, it is done in two phases. So first we'll discuss the phase 1, then we'll go to the phase number 2. So in phase 1, it is the derivation of an equivalent grammar G dash from the context-free grammar G such that each variable derives some terminal strings. So the procedure to do that is, step number 1, include all symbols W1 that derives some terminal and initialize I equal to 1. So we have our context-free grammar G, and from that we will make a set of symbols which we will call W1 that will contain the symbols that can derive some terminal symbols. So those we will keep in our set W1, and then we initialize I equal to 1. Okay, and then in step number 2, we include the symbols Wi plus 1 that derives Wi. So in the previous step we had the set of symbols that derive the terminal symbols, and in the next step we will make another set of symbols which can derive the symbols that were present in the set of the
बच्चों के लिए क्या है 3 साल लाजवाब में जो कि चलेगा 27 में से 2
previous step. All right, and then we will increment I and repeat step 2 until Wi plus 1 equal to Wi. So we will increment I and we will repeat this step number 2 until we reach a stage in which the two consecutive steps produce the same kind of sets. If the elements of the sets in two consecutive steps are the same, then we stop the process, and then we include all production rules that have Wi in it. So after getting this final set Wi, from there we will include the production rules, all of which contains the symbols in the set Wi. So that is phase number 1. So don't worry, even if it sounds a little confusing, it will become very clear when we take the example. Okay, so now let's go to phase number 2. So phase number 2 says derivation of an equivalent grammar G double dash from the CFG G dash such that each symbol appears in a sentential form. So we have already obtained the grammar G dash using our phase number 1 from the original grammar G, and from this G dash that we have obtained in phase number 1, we have to derive another equivalent grammar G double dash such that each symbol appears in a sentential form. Now how do we do this? Let's see the derivation procedure. Step number 1. Include the start symbol in Y1 and initialize I equal to 1. So we form a set which we will call Y1, and in this Y1 we will include the start symbol of our grammar, and then we initialize I equal to 1. And then step number 2 says include all symbols Yi plus 1 that can be derived from Yi and include all production rules that have been applied. So just like we did in phase number 1, even in this one, we see that in Y1 we have our start symbol, and then in the next step we will include all the symbols in the set of the next step that can be derived from the symbols in the set of the previous step. So here our previous step contains the set containing the start symbol. So in the next step you will include all the symbols that can be derived from the start symbol. That will be your Yi plus 1. and then increment I and repeat step 2 until yi plus 1 equal to yi. So you will continue doing this. You will continue including the symbols that can be derived from the symbols in the previous set of the previous step and make new sets until you reach a stage where two consecutive stages or steps produces two sets of containing the same symbols. At that time you will stop the procedure and we will include the productions that we obtain in the last set yi. Okay, so that is the phase number 2, and following this phase 1 and phase 2 we can obtain the reduced context-free grammar. Alright, so now we will see an example to understand it in a better way. So here we have an example which says find a reduced grammar equivalent to the grammar G having production rules, this one. So we are given a grammar G and we have a production rule which says S gives A, C and B, and A gives A, C gives C and B, C, and E gives A and E. So here the start symbol is S and the non-terminal symbols are A, C and B, and the terminal symbols are small a, c and small e. So we have to find a reduced grammar for this. So we will follow those two phases which we have studied in the beginning. So let's proceed with phase number 1. So in doing phase number 1, we have to first find out what are our terminal symbols. So as I already mentioned, our terminal symbols are small a, small c and small e. These are our terminal symbols. And now we have to make a set W1 in which I will include all the symbols that can derive the terminal symbols. So what are the symbols that can derive the terminal symbols? Let's see. So here we see that S does not derive any terminal symbol, so we can leave S, and we see that A derives the terminal symbol small a, so I will include A in this, and then C also derives a terminal symbol, so C will be included, and E also derives a terminal symbol small e and also small a, so E will also be included. So I have my set W1. Now I have to make a next set W2 in which I have to include all the symbols that can derive the symbols present in the set W1. So in W2 I have to include the symbols that can be derived from the set W1. So what are they? A, C and E will all obviously be there, and let's see if there are any others. Let's check the start symbol S. So we see that the start symbol S can derive A, C, and AC is present in the set W1. So we have to include the start symbol. So ACE, let me write them as they are, and then we have to include the start symbol S. Okay. Now let's do the same thing again. W3 we will do the same thing. We have the symbols A, C and E. So it is the same thing, A, C, E and S. So we find that in two consecutive steps, W2 and W3, we are getting the same kind of symbols in the set. So we can stop this procedure. So this is the final set W3 that we have obtained. Now we have to see how can we write our grammar. So our grammar G dash can be written as, what are the non-terminal symbols? A, C, E and S. Okay, these are our non-terminal symbols. And what are our terminal symbols? Here the terminal symbols that we will have are A, because A derives A, and then C derives small c, okay, and E derives, what does E derive? E derives small e. So this will be our terminal symbols. S does not derive any terminal symbol. And then P is the production rule which we will write now, and after that we have S, which is the start symbol. Okay, and then let us define the production rule. How do we define it? Production rule will be given like this. Let us start with the start symbol S. Here we have S, and here we did not have B in any of our sets over here, so B will not be included. We will only use the production rule which says S gives AC. And then we have A. For what does A give? A gives small a, and then we also have C, which gives small c, and then we have E, which gives small a, and also E. Okay, so this is the production rule for our grammar G dash, which we have obtained from phase number 1. Now let us proceed to phase number 2. In phase number 2, we have to look at the grammar G dash that we have produced. So our first step was to include a set Y1 in which we will include only the start symbol, which is S. Okay, and then in Y2 we will include all the symbols that can be derived from the start symbol S. So what are the symbols that can be derived from the start symbol S? We see that S can derive A, C. So A and C also should be included. So S is there, and then A, and then C. Okay, that is from this production rule. And then in the next step, which is Y3, we have to include all the symbols that can be derived from these symbols in the set Y2. And what are they? We see that S derives AC. AC is already present, and we have A here, and we see that A derives A. Okay, so S is there, A is there, and C is there as they are. Now what are the new ones we have to include? A derives small a, so I derive small a, and we have C. And what does C derive? C derives small c. Okay, so these are the things we have to include. And if we do one more step, Y4, we'll see that there will be no change. What are the symbols that can be derived from these symbols? They are only S, A, C, small a, and small c. So these are the only symbols that can be derived. So we get these symbols, and we see that in step Y3 and Y4 we are getting the same symbols in both the sets Y3 and Y4. So we can stop the procedure. And now we have to define our grammar G double dash. Non-terminal symbols are A, C, and S. This one. See, we see that we have A, C, and S here. And then what is our terminal symbols? Only A and C are the terminal symbols. And what is the production rule? We'll call it P, which we will define. And then we have S as our start symbol. Okay, so this is the grammar G double dash that we have. Now we have to define the production rule P. So in order to define the production rule P, we have to see what are the symbols that we have. We have A, C, and S. Now let us start with the start symbol S. S, what does it derive? S derives A and C. A and C, that is all what we used. And then what is the next one? A. What does A derives? A derives small a. And then we have C. What does C derive? C derives small c. So this is the new production rule for our grammar G double dash. So now we have the reduced grammar G double dash, which is a reduced form of the grammar G which was given. So if you notice, you see that in the original grammar, this was the production rule. It was a long one. Here we also had E, and we also saw that C was giving C and also BC, and S was giving AC and also B. But if you look at the reduced grammar that we have, we see that S gives only AC, A gives A, and C gives only small c, and E is no longer there. So this is a simplified and reduced form of the given context-free grammar. So this is the way you reduce the CFG. So I hope that was clear to you. And in the next lecture, we will be studying about the removal of unit productions, followed by the removal of null productions. So thank you for watching this one, and see you in the next one. In this lecture, we will be studying about a derivation tree. A derivation tree or parse tree is an ordered rooted tree that graphically represents the semantic information of strings derived from a context-free grammar. So we have already studied about context-free grammar, and we have an idea about context-free grammars. In this lecture, we will be studying about simplification of context-free grammar. So in context-free grammar, sometimes all the production rules and symbols are not needed for the derivation of strings. Besides this, there may also be some null productions and unit productions. Elimination of these productions and symbols is called simplification of. Each contains only one type of symbol. So what do I mean by this? I'll show you. Free languages. In the last lecture, we have studied about pumping lemma for context-free languages. And in this lecture, we will be taking an example to see and figure out how the pumping lemma for context-free languages actually works. So here we have an example language given, L equal to A power n, B power n, C power n, where n is greater than or equal to 0. So the meaning of this language is that we can have symbols of the form A, B, C, and then the number of A's should be equal to the number of B's, and it also should be equal to the number of C's. That means if you have n number of A's, you should also have n number of B's and also n number of C's. So it means the number of A, B, and C should always be the same. That is the rule of this language that we have. So our task is to show that this language is not context-free, and we will do this using pumping lemma for context-free languages. So let's see what are the steps that we need to follow. So the first step is we will assume that the language L is context-free. And why are we doing this? We studied in the previous lecture that the way we are going to prove this is using contradiction. So first we will assume that L is context-free, and we will show that there is a contradiction to our assumption, and hence it is not context-free. So we'll see how we do that. So first we have this language L and we assume that it is context-free. So if it is context-free, then the language L must have a pumping length. This also we studied, and we will call the pumping length P. And now we will take a string S such that S is equal to A power P, B power P, and C power P, where P is our pumping length. And then we have to divide S into 5 parts, U, V, X, Y, and Z. So let us just look at the rules of this pumping lemma that we studied in the previous lecture, just to recall those. So this is the rule of pumping lemma that we studied in the previous lecture. And we said that if a language is context-free, then it will have a pumping length. So we already assumed that our language is context-free, so it will have a pumping length P. And then we have to divide our language into 5 pieces, U, V, X, Y, and Z, which we will do. And after dividing that, you have to show that U, V raised to I, X, Y raised to I, Z also belongs to the same language for every I greater than 0. So this condition must hold if the language is context-free, and also condition 2 and 3 must hold. So we will focus on condition number 1. So let's go back to our problem. So here we have taken P as our pumping length, and we are going to divide our string S into 5 parts, U, V, X, Y, and Z. So let's see how we can do this. So here, for example, I have taken the pumping length P is equal to 4. You can take any other length also, but here, for example, we have taken our pumping length P, which is equal to 4. And so we have the string A power P, B power P, C power P. So all the P's I replace it with 4. So I have my string of the form A power 4, B power 4, and C power 4. So this is the string that we have, and our next step is to divide the string S into parts U, V, X, Y, and Z. So let's see how we can divide it. There are 2 cases. Case number 1. V and Y each contains only one type of symbol. So what do I mean by this? I'll show you. So here I've taken this string A 4 times, B 4 times, and C 4 times. So this is the string that we have. Now I'm going to divide it into U, V, X, Y, and Z such that V and Y each contains only one type of symbol. So let's see. I will take these 2 A's. This part will be my V. And then I will take this C over here, just this one C, and this will be my Y part. So what will be the remaining one? This A over here, this is my U, and this A, B, 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 and up to this C, this is my X, and this 2 C's over here, this is my Z. So I have divided my string into U, V, X, Y, and Z. And the case that we had was that V and Y each contains only one type of symbol. So where is my V? This is my V, and V contains only A, the same kind of symbols. And what about Y? Y also contains only one kind of symbol, which is C. So each V and Y, it contains only one type of symbols. So that is one case or one way in which you can divide it into parts u, v, x, y, and z. Now after we have divided, we said that the condition number 1 was saying that u, v raised to I, x, y raised to I, z must also belong to the language. So here I have I over here, and I am going to take I is equal to 2, for example. So if I take I equal to 2, that means it will be u, v square, x, y square, and z. Now let me replace it here and see what is the kind of string that I am going to get. So if I do this, u, what is my u? U is just 1a. And what is my v? V contains 2a's, but it is v square, so I have to double it. That means there will be 4a's. A, 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 A. Then x. What is my x? A, B, 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 C. A, B, 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 C. And then I have y square. What is my y? Y is just 1c, but since it is square, I have to double it, so there will be 2c's. And then z. Z contains 2c's over here. C, C. Alright, so this is the string that we get. Now let me count how many a's are there. 1, 2, 3, 4, 5, 6. There are 6 number of a's, and how many b's? 1, 2, 3, 4. 4 number of b's, and 1, 2, 3, 4, 5. 5 number of c's. So
did you know that 80% of the top Fortune 100 companies use Asana?
is, and that is also is 5. The number of a's is not equal to the number of b's, and that is also not equal to the number of c's. So the rule of our language said that the number of a's, b's, and c's should always be the same. But when I divided my string into u, v, x, y, and z, and when I raised this v and y to the power of 2, the string that I am getting does not belong to the language L, because the resultant string that I get here has different number of A's, B's, and C's. So this does not belong to the language L. So this shows that condition number 1 cannot be satisfied. So since condition number 1 cannot be satisfied, we see that our assumption which said that L is context free does not hold. It is a contradiction to our assumption. If L was supposed to be context free, then the string that I get here should also belong to the language L, but it is not belonging to the language L when I do this. So our condition number 1 itself fails. If you want, you can check conditions number 2 and 3 also, but since 1 already failed, so there is no point in actually checking 2 and 3. So from condition number 1 itself, we found that it is a contradiction to our assumption which said that L is context free. So we can say that L is not a context free language from case number 1. Now we can have another case. Let's see what that is. Okay, the case number 2 says that either V or Y has more than one kind of symbols. So this is my string, 4 number of A's, 4 number of B's, 4 number of C's. Now I'm going to divide it into 5 pieces, U, V, X, Y, and Z, such that either the part V or the part Y has more than one kind of symbols. So let me see how I can do this. So here, this one, the rules that we studied in the previous lectures, which are used to prove that a given language is not context-free using the pumping lemma for context-free languages. So first we say that if A is a language and if it is context-free, then it needs to have a pumping length P such that any string that belongs to the language where the length of the string is greater than or equal to the pumping length can be divided into 5 parts U, V, X, Y, and Z such that all these 3 conditions must be true. And in the last example,
ये देखो।
Example, if you remember, we were focusing on condition number 1 and we did not really focus or we did not really check if condition number 2 and 3 were true or not. But in this example, what we will do is we will first make sure that conditions number 2 and 3 are true, and then we will check if condition number 1 is also true or not. And then we will see if all these three are true, then we can say that the language is context free. And if any of them is not true, it says that the language is not context free. So first, remember this conditions 3, which says that the length of v, x, and y should be less than the pumping length. It should be less than or equal than the pumping length. And also the length of v and y should be greater than 0. Alright. And then when you raise v and y to the powers of I, then the resultant string that we get must also lie in the language that we have. So let's see if these three conditions will be satisfied for our given language. Alright, so we come back to our example, and what is the first step that we need to do? We need to first assume that L is a context-free language. So first we will assume that L is context-free, and then we will show that there is a contradiction to our assumption, and hence we'll prove that it is not context-free. So first of all, we will just assume that L is a context-free language. So if L is a context-free language, then L must have a pumping length. Let's call it P. Now we have to take a string S from our language L. Now how will we take this string? I already told you that this language L can contain strings of the symbols 0 and 1. So I take my string like this: 0 power P, 1 power P. So this is my first W. And then if my W is 0 power P, 1 power P, then my second W should be exactly the same. So since this is 0 power P, 1 power P, the second part also should be 0 power P, 1 power P. So we see that the first half is exactly equal to the second half, which is a property of our language L. So we have this string S, and now we have to divide our string S into parts U, V, X, Y, and Z. Now we have to divide this into these 5 parts, and let's see what are the possible ways in which we can divide our string S into parts U, V, X, Y, and Z. Alright, so first we will take our pumping length as 5. We assume that our pumping length P is equal to 5. So if P is equal to 5, then we have 0 power 5, 1 power 5, and so on. So if I expand and write it here, this is how my string looks like: 5 number of zeros followed by 5 number of ones followed by 5 number of zeros and 5 number of ones. Now let's look at case number 1. Case number 1 says that when you divide it into parts U, V, X, Y, and Z, the part V, X, Y does not straddle a boundary. Now what do you mean by straddle? Straddle means that it does not lie on either sides of a boundary, but it just lies in one part. Now let's see what are the boundaries that we have here. So here 0, this is one boundary, and the 1 ends here, this is another boundary, and this is another boundary. First boundary, second boundary, third boundary. Now the part Vxy, it just lies in one part. It does not cross this boundary, nor does it cross this boundary. It just lies in one part. That is what I mean by Vxy does not straddle a boundary. Now this is one way in which we can divide our string into these 5 parts. Now if we have divided into these 5 parts, and let's see if condition number 3 is holding, v, x, and y. What is the length of v, x, and y? It is 1, 2, 3. And is 3 less than our pumping length? Yes, our pumping length is 5 and it is less than 5. So condition number 3, it holds. And condition number 2 says that the length of v and y should be greater than 0. That is obvious from here. And condition number 1, that is what we have to check now. In this lecture, we'll be studying about
ये कौन है? तो गाइस अब नमाज का टाइम है, 10 मिनट का ब्रेक लेते हैं। नमाज है, थोड़ा सा वर्कआउट करता हूँ मैं, सम डम्बल्स एंड सम नमाज।